Are we okay? Yes.
So at this point, what's happening with it, it's pushing this way because of the heat. The wall's pushing back, so it's
As a
actually
form.
starting to
Yes.
form.
Yes. Yes. Okay. So now for the color one is this. Due to the existence of the RE, then let me put into this way. For the RE, the model will be something like this. This is reaction force. And let me change the color. So this is X. So for this case, this is 0. So RE is here. And so for this blue, the model in the blue color, that is RE is to compress throughout the two sections. So that means here we can tell using our P over EA, for the first segment, the force is RE, and L is 0.3 meters. E equal to 200 times 10 to the 9th, and A times pi over 4 and 0.04 meters squared. For the second segment, the force is RE times 0.2 and 105 times 10 to the 10 to the 9 and 0.4. Okay, and that is the deformation caused by the reaction RE, and that is how much? Is this much, right? And what is that? That is 0.495 times 10 to the 4. So this is 0.495.
Wait, what is that?
0.495, yes.
Right, shouldn't it be 4.95?
Isn't it 6.15 minus 7.2?
Oh, let me double check. Oh, so that should be 4.95, right?
Yeah.
Thank you.
Why did it go from 1.2 where you're at the gap?
Oh, the 0.12 is the gap.
Okay.
Yeah.
Wait, can you do the math on where the 4.95 is coming from?
Oh, yes. So simply, the distance is the whole thing minus this one. So 0.15 minus.
That's not 4.95.
Oh, this is 1.2. Sorry.
Okay.
Yeah. So from here we can solve for RE. RE equal to 127.35 kilonewton. And again, in this calculation, the unit on the right-hand side will be in meters. Okay, so you have to take care of the units for the reaction. Actually, reaction calculated RE should be in newtons, and here I converted it into the kilonewtons. So this is this number, and RE apparently that is compressive. Okay, so that means in terms of the task, we should put on compressions. And put this word, okay? Okay, now we have come to this one. So reaction at RA, that means is this case. So this is the thermal loading have been loaded up, and here we have calculated RE. And RA simply is equal to RE in balance. So the reaction RA, that should be RA equal to RE in magnitude. So that equal to 1.7. Now the second one, displacement at C. The same thing, we'll look at the model here. Again, from the two colors mode, and here the red one, the whole situation is this. The red one is assuming that the free expansion. And then due to existing RE, that push back the free expansion by that much. So that means in this case, this number is what we're looking for. Right? Are we okay? And then what is this? We've been calculated. That is this number. This represent is the thermal deformation of the first segment. Thermal deformation of the first segment. This number. Anyone can help function this number for everyone? About 2.6 times
2.81 times
10 to the negative 4 meters. Okay, so this one is 2.81 times 10 to the minus 4. And then what is this? This one represent is from the blue model. The blue model is pushed back the RE, so that is the change in the deformation due to reaction RE in the first segment. So that is this amount. Are we okay? Can you see it? And what is this number? This is. Let me write it up here. So this number is 1.19 times, no, I don't have the numbers. Who can calculate this for me? 1.19 times reaction, 127 times minus 6.
Wait, where's the is that the reaction force? Or the,
Yeah.
Well, what is it? Oh, the 1.1.
Yeah, 1%.
Wouldn't that be 10 to the third? Because that's in kilonewtons.
No, why not you just calculate this one for me? Then I will put the numbers here.
151 times 10 to the minus.
151. Thank you. Okay, so this blue one is 1.51 times 10 to the minus 4 meter. So what is displacement C? That is this amount, right? And that amount simply is the difference between that one. So that would be equal to 1.3 times 10 to the minus 4 meters.
Where are you getting the 1.51 times 10 to the negative 4?
Oh, I simply plug in the RE into this term.
Okay.
Yes. And here I have a formula, but I don't have a calculation. Simply we plug in the RE into this term to calculate this one. That will be equal to this. Okay, so the answer is this one, the magnitude. So displacement has a magnitude equal to this. It's moving which way? Right way or left way? So basically here how about that? We say rightward is the net positive, this is the leftward, that is the negative. So we take the sign convention, so in total net value is this one, this is right way, right? Are we okay? And this is pretty much the thermodynamic if we have a few minutes, I can try to find the smaller example to try. Any questions about this before I erase this space? If no, one more time? No? Okay. Another example is this. If we have a different material, for example, this is E1, this is E2, and they have the same length, and different CTE, and different cross-sectional area. So again, for this case, we consider a thermal loadings. We want to calculate what is the deformation.
Are they connected or is one?
They glued well. There's no fractures, no cracking during the thermal loading. So basically, the two materials are, you could imagine this is a laminate, okay, using glue or using whatever the welding, basically the two materials basically stick together.
So one stretches is going to hold the other.
Yes. And this one, we can imagine is this. So let me redraw this one here. Assuming, to think about this question, we're assuming there's a different strategies we can try. And here, let me introduce the simplest one. What we could imagine is, say, for example, the two materials, basically they're free from each other to move. So in this way, say, assuming the, how about, let me give a number, say, assume that alpha 1 is greater than alpha 2, okay? So that means this material, if they're free to move from each other, so this will deform. By that much. So this much will be equal to, let me use this delta. This is material 1, material 2. This is the thermal expansions of the first material. And assuming they're free to move from each other, so this will be the second deformations for the thermal deformation for the second material. However, they glue together. So basically, there's a tug of war or competition between existing here. So that means their final positions, equilibrium position of this side must be falling in between. And in between somehow, let me say, is here. So this is their final equilibrium position of side, let me call B. So if this is side B, this side A. Are we okay?
So you can't just assume that the alpha of the weaker material
I have
governs.
to assume one is larger than the other one. If they are equal, then basically they expand at the same amount.
Right.
If the alpha 1 is less than alpha 2, then this thermal expansion will be less than this one.
Right.
Okay.
But you can't just say that it's going to automatically be the weaker one.
The weaker one, the weaker is kind of tricky. Yeah, so right now we just stick with this one. Okay. So for this case, then we can do this. So you can see right now because the interface been so grouped well, so that will exist the reaction. That reaction will be actually is this. Reaction on material one is to push back. Let me call the reaction R. The reaction is to push back this amount by that much. And action reaction from here to the same amount of the reaction here, we're going to push longer to the equilibrium. Right? So that is how much is?
So that's the same force, that's R.
Yeah, so let me call this is due to the reaction of the material one. And let me call this amount, this R. This is the reactions on material 2. Before we formulate into detail of each term, that should be like this, right? So in this way, you can look at here, delta T1, we simply look at the geometry, delta T1 minus this one. So basically, let me look at the dimension here, from here to here. That amount on one side for the material one is this. On the material 2, that amount is equal to this. Are we right? So that is maybe back to your questions. This is very critical. If this number swap, if this will be less than this one, then the formulation will be right away changed. Okay. And then what is this? Now we formulate the information one by one. Thermal deformation for material 1. We simply plug in our fundamental equations. Alpha 1 times delta T times L. And what is the thermal deformation for 2? That is alpha 2 times delta T times L. And then what is the deformation due to reaction? And that is our generic formula, RL over EA. Right? And then for the R2, RL over EA. And please pay attention, all the numbers here are magnitude. Because whether they are negative or positive, I don't care, because here we have formulated is in terms of the geometry. So right now, this equation here already taking care of everything. So once you do the calculation, plug-in always is plugging the numbers into individual terms. And by which you should be able to solve for R. Okay, and coming Monday, we will try maybe one or two more problems.